Not in the mood for beating around the bush today. Let's go.
Code trashification. What can I do?
Part 1. Word to vec. Last time we were vectorizing sentences, now we'll vectorize words. We will build a matrix that maps one-hot encoded tokens to fixed size vectors. Multiplication by a one-hot vector can be thought of as selecting a row in the matrix. A common way of creating one of these is with the skipgram method. A skipgram model receives the central token and tries to predict one of the neighboring ones within a context window. As usual, I begin by tokenizing the dataset. As usual, this will be my downfall. A token is either some alphanumerics or some punctuation. I also add 4 special tokens: beginning of sentence, end of sentence, padding, and unknown. This dataset sucks, by the way. Most of it is the same few sentences. From these tokenized sentences, I create example pairs of tokens to train the skipgram. This dataset is small and not very diverse, so training is easy and fast. The process of training the model should push similar tokens closer together in the embedding space. Here's a visualization via principal component analysis. It seems to reflect the shape of our dataset pretty well. Frequently co-occurring words did in fact end up in constellations. Now that we've vectorized our words, we can work with them via machine learning methods. Part 2. The transformer. The aim of this section is to create a model that can translate English to German, or to die trying. I'm using the 2019 WMT News dataset. The description says to give a citation. It's linked in the code. I keep as many words in my vocabulary as possible because I don't really want my model defaulting to the unknown token too often. Before creating the transformer, I pre-trained the embeddings. This should give our model some useful information to work with at the outset. I rewrote my skipgram to take advantage of a more efficient implementation from PyTorch that bypasses the one-hot representation. This saves memory and allows us to reach crazy batch sizes. Even in such a small dataset, we have enough distinct tokens to push our parameter counts into the tens of millions. I trained skipgram models for both the English and German half of the dataset for a combined total of 15 minutes. Now we have to build a transformer piece by piece. Luckily, I've been able to rely on some very nice example implementations. My favorite one was the Harvard annotated transformer. The first thing I implement is positional encoding. For each distinct position in the sequence, a certain constant vector gets added to the token embedding. The model should learn to pick up on these to distinguish the order of tokens. Up next, the star of the show, the attention mechanism. Each token is assigned a value vector, which represents some information encoded in the token, a key vector and a query vector, so that every other token compares its query vector to the key to see how much information it needs to take from the value vector, and a context vector, which is a linear combination of every value vector. Stacking all of these vectors into respective matrices, we can write down the attention operation as 2 matrix multiplications and a softmax. A mask is usually applied to the query key product to prevent the model from looking up information where it doesn't need to look, like after the sentence is over, or in future tokens of the sequence. Up next, as machine learning engineers, we want to run multiple of these in parallel. This is what multi-head attention is for. It slices all of the vectors and performs attention in the resulting subspaces, then concatenates everything back together. It also runs the reconstructed context vectors through another linear transformation to mix around the information from the subspaces. If we shuffle our tensors right, we don't need to loop over the heads. We can compute everything in parallel. Queries, keys, and values can either come from the same sequence, which is called self-attention, or in cross-attention, queries come from a different sequence. Now we can slap everything together. I'm using the same architecture as in Google's 2017 paper, Attention is All You Need. A sequence-to-sequence transformer consists of an encoder, which reads the source sequence, a decoder, which interprets the encoder's outputs given the target sequence so far, and a generator, which turns the decoder's output into a probability distribution for the next token. After instantiating this monstrosity, I load in the pre-trained embeddings. Training takes like an hour, After each epoch, I save a snapshot of the model. Looking at the training and validation perplexities, we can see that the model struggles to generalize and overfits at the end, which I probably should start expecting by now. The snapshot with the best testing perplexity gets loaded in for the final evaluation. So far, inference has relied on teacher forcing, in which the decoder is fed a reference sequence, which it only has to continue by one token at a time. In the real world, we usually don't have reference translations for things. From now on, the model will auto-regressively make up its output as it goes along. The result is bad, but funny. Grammatically, it's passable, but it's nonsense.
What is this? You look at your code, you look at the trash bin, you throw in the trash bin.
The model seems to have memorized the approximate distribution of words in the German half of the dataset, without forming a strong connection to anything in English. Unlike the model built by the guys at Google, ours doesn't have a unified word embedding that spans across languages, which would connect their meanings. We need to report a final number for translation quality. This is hard, so I let the clever guys who wrote Blue do it for me. Blue, the bilingual evaluation understudy, compares reference and hypothesis sentences based on the clipped n-gram precision for n up to 4, with an additional coefficient that punishes overly short translations. At the corpus level, it does something really contrived instead of just averaging the scores, so I won't get into it. All we need to know is that a score of 1 is extremely unlikely, 0.3 is considered good, 0.4 is considered excellent. After running inference for like 5 minutes, 500 to 1000 milliseconds per sentence, we get a final blue score of 0.17 something. It could have been worse. By rambling, the model takes advantage of Zipf's law and eats the imprecision penalty. For reference, the guys at Google got 0.284, which was better than state of the art at the time. They also had 100 times the data, 10 times the time, and a way better tokenizer. Now that it's all been said and done, I don't feel much of anything at all. I usually expect better from myself, but I have to move on. For now, bye.